really happy to be here and have the opportunity to speak at the OWASP 20th anniversary. So hi everyone, my name is Edwin Kwan. How many of you have heard about a security incident in the last few years? Now, I remember recently reading about the security vulnerability with the Confluence servers. There was a vulnerability in Confluence's tag system, which allowed remote code execution. It seems like the number of security incidents and data breaches are increasing, and it feels like not a month goes by without hearing of yet another breach or compromise. Are we getting worse at doing security? And whenever there is a security vulnerability, developers are usually the first to be blamed. We'll say things like, hey, they use a vulnerable open source components, or there was a misconfiguration in the application. However, is it really the developer's fault? So for this presentation, I'd like to share my opinion on this from an application security perspective by taking a look at how software development has changed over the years. Let's take a walk down memory lane. Back 20 years ago, I believe this was the time when the Nokia communicator was all the rage. For this presentation, we're going to look at the software development lifecycle journey for a fictitious company, Acme Corporation. Though the company is fictitious, its journey should be somewhat representative for most typical organizations. So I'd like you to meet Sam. She works at Acme Corp as a software developer, and she does all her coding in Java, and she's part of a software development team. Sam and the team receive requirements from product for the software they need to build. Those requirements come upfront, and they have expected delivery dates that are a couple of months away. Once she receives those requirements, she and her team will work out the design and the implementation details. There might be a software architect involved, and they will determine how to build the application as per product's specification. Everything is one big application back then, and her deliverable is a jar file. Security was the Department of No back then, so they usually have to build everything. This included the authentication mechanism, the login functionality. There were not many third-party services allowed back then. As the expected delivery date draws near, there is a product verification phase. Here, the application is put through rigorous testing to ensure quality assurance. This is usually done by another person or team, and there are a number of test objectives and test cases drawn out for what needs to be checked. And from memory, it's a pretty formal process, and there is like an official test report provided at the end of the activity. And in that report, it will contain all the issues that Sam and her development team will need to address before they can deliver their application. On top of QA, there's also security testing that's being done. Sometimes the security testing and QA are combined together. The security testing would check that there are no security bugs. It would verify the access controls. It would ensure that the whole system where the application runs off has sufficient perimeter defense and that it is adequately security hardened. Once that is all good, the deliverable, which is the jar, is handed over to the operations engineer, who would follow the installation instructions to deploy the system into production. Now, this is usually a physical server, either in their own data center or in their customer's data center. If there was a problem with the installation, there were usually procedures available for rolling back the system to its previous state. Once this jar is delivered, the development team is usually no longer involved with that application. From here, it is the operations team who is responsible for the maintenance of the system. This includes performing any upgrades or patching that is required. So that's how software development looked like at Acme Corp 20 years ago. It takes a couple of months to deliver a product, and the development of it involves a number of teams. There's the development team, the testing team, the operations team, and there's the security team. Now, let's look at how that evolved 10 years later. So we're now going from how software was developed from 20 years ago to 10 years ago. And I believe that this is the BlackBerry era. There were a few major changes that happened during that time. First, projects at Acme Corp were consistently late and not meeting deadlines. To address that, the company decided to shift towards agile development. The benefit of doing that is shorter release cycles, and the teams are able to continuously deliver value to their customers quicker. This is a great idea. They're able to get feedback from their customers early and are able to make any required changes along the way. What this means, though, for Sam and her team is that rather than releasing every few months, they're now releasing every few weeks. Now, there are some challenges with having that many releases. There's typically more developers than there are testers, and having shorter release cycles means there needs to be there needs to be faster feedback from testing. So Acme Corp decided to adopt test-driven development, also known as TDD. This is where software requirements are being converted to test cases before the software is fully developed. The idea is to write a failing test to capture a software requirement. You then write the simplest bit of code to get that test to pass. Next, you refactor the code and you repeat by writing a new test. This is a big change from what they did previously, where software was developed first and test cases created later. As a result of this, testing is now something that is done by the developers, and the testers in the team became quality advocates, coaching developers on how to do testing. This is a great step forward, as there's now faster feedback when software requirements are not being met. And because there are test cases capturing each and every requirement, there is immediate feedback should a change break some of those functionality. The next change was the move towards virtual machines and microservices. Deploying on physical machines was time-consuming, and the operations team were constrained by the procurement process and the installation of those physical servers. Moving to virtual machines allowed new VMs to be very easily configured and spun up, allowing it to keep up with the more frequent deployments that are now happening. And with the shift towards a microservices architecture, it brought many benefits. Rather than deploying one big monolithic application, they're now deploying multiple, much smaller microservices. This provided many benefits, such as allowing the system to be independently deployable, so you can deploy the front-end services independently of the authentication service. It also allowed loose coupling, which means that each service is not overly dependent on how the other services are defined or implemented. And because they're using an agile methodology, this is how it would look like using a microservices. So for the first iteration, you'll be building a skateboard. So it has minimum microservices, and they're all on version 1. With the next iteration, more microservices are deployed, and some of the existing microservices might get updates, which is indicated by the increase in the version number. The next iteration, same thing, more microservices deployed, and some of them gets updated, and so forth, until you get to your final product. One of the changes with using a microservices architecture is that instead of delivering a single jar, there's now multiple jars involved. And all those microservices will need to be maintained. So that's how software development looked at Acme Corp 10 years ago. Instead of deploying every couple of months, Sam and her team now deploys every few weeks. And every deploy is delivering value to the customer. And because they're using a microservices architecture, they're now building multiple microservices. And as they are doing TDD, they're now wearing the testing hat and making sure that the software they deliver contain no bugs and that it functions as per requirement. They still have the operations team who's now looking after a bunch of virtual machines, and they are responsible for making sure those virtual machines are security hardened. And you still have the security team who's managing access control, looking after the perimeter, and also performing security testing to find any bugs. Now, we're up to looking back at the last 10 years, which has seen some drastic changes in software development. So Edwin Corp decided to embrace DevOps, and they moved to a you build it, you run it model. They felt that the previous model wasn't ideal, as you had the development team, which was very focused on delivery, and then you got the operations team who were tasked with maintaining the existing deployments, and they were focused on stability. And the two teams, delivery, stability, were often in conflict. So with DevOps, they brought the development teams and the operations team together with the intention of improving deployment frequency and shortening the lead time between fixes. And for most organizations, there are many more people in the development teams than there are in security. So with the shift to DevOps, the security team is now unable to scale to keep up with the faster release cycles. That's when we introduce DevSecOps, where we look at shifting security left and making it the developer's responsibility. So now it's the model of you build it, you run it, and you also secure it. So in order to do DevSecOps, security training was provided to the development team. This was in the form of either online self-paced learning or a classroom-based training. The training taught developers how to write secure code and identify common vulnerabilities. There was also the introduction of security tools to help identify security issues. This included static code analysis, software composition scans, and dynamic code analysis. And those tools were integrated into the build pipeline so that they could be automated and provide early feedback to the developers. The security team used to be the Department of No. However, that has since changed. And now there is a great uptake of open source software. The graph here shows the number of Java downloads, and it shows that the usage of open source has significantly increased. And this graph shows the increase in open source for Java, JavaScript, Python, and .NET in the last year. So open source is great. It helps speed up development by providing functionality that the teams would otherwise have to write themselves. This allows them to go to market faster. To get an idea of how much open source we're using, I did an analysis on some of the apps within my organization. For one of the apps, we had 12 components that were written in-house. This was a Java Maven application. So these 12 components consisted of submodules and internal libraries. How many open source components do you think it used? 50? 100? It used 268 open source components. And if you do a comparison just by the number of components, the open source components make up 98% of the application. If we did a comparison by file size, we would also get around the same percentages. And I found similar ratios with the other applications that I analyzed. So what this means is that today's development teams only write a very small percentage of the code that makes up our application. You can almost say that today's development teams are now assemblers rather than builders. So for Sam at Edwin Corp, she's now only writing a very small percentage of the company's software. The majority of it is written by some other developers who build those open source components that her systems are using. Now, not all open source are created equal. And In a state of software chain, a supply chain report, it was found that around 10% of open source components that were being downloaded contained known vulnerabilities. The last 10 years also saw the move to the cloud. This provided a lot of flexibility to Acme Corp. They now did not need to rent out space in the data center or make capital purchases on their physical servers. That was all outsourced to the cloud providers. They could also easily scale up their resources or scale down when needed and only pay for what they use. As their systems are now no longer physically behind their firewalls, they do need to be extra careful now with how their cloud infrastructure is configured. Because if done incorrectly, everything is potentially publicly accessible. I remember an example of this, and this was with the AWS S3 buckets. They had permission issues. This was a few years ago. And the issue was that when you set the access to authenticated users, it didn't do what users thought it would. And rather than restricting permissions to authenticated users within their organizations, it allowed any AWS authenticated user access to that bucket. Then there's also the move to containers. This was a huge benefit to Acme Corp, as container users use fewer resources to run. And this allows for the reduction in overall infrastructure resource. It also reduces deployment time, as containers are configured to maintain all configuration and its dependencies internally. This allowed the developers to take their own configuration, put it into code, and deploy it without any problems. There are additional security responsibilities the developers are now taking on with this. They need to ensure the containers are safe, that it is not a poison image. They need to check that the containers do not contain versions of software with known vulnerabilities, and they need to security harden the containers and remove any unnecessary programs. They are now responsible for the security configuration and patching of the software running within the container. They've taken on some of the responsibilities that would have normally be on the operations or the infrastructure team. And there's also the move towards infrastructure as code, using open source frameworks like Puppet, Terraform, Chef, and Ansible. With the move to cloud native, we're also shifting our thinking from securing the perimeter to having a zero trust network. And because we've moved to infrastructure as code, a lot of those security group configurations and policies are now the responsibilities of the developers. In addition, they also need to do secrets management and identity and access management. That's a lot of security responsibilities they are now undertaking. And if any of those are done incorrectly, it can result in a breach. This graph here is taken from the 2020 Verizon data breach report. It shows the different actions that result in breaches over the years. You can see that physical breaches have stayed relatively the same. Hacking, social, malware, and misuse have all decreased in the last few years. The only action type that is consistently increasing year to year in frequency is error. The fact is that people can, and they frequently do, make mistakes. This next graph here shows the different types of errors and their trend in the last few years. It shows that misconfiguration errors have been increasing. Could this be correlated with our move towards cloud native? Here's an example of a misconfiguration error that was discovered during a pen test that we did last year. It was on a Kubernetes Istio-enabled deployment. And this application had a sidecar which handled all incoming requests. And this sidecar was an Envoy proxy. This application accepted HTTP requests from authorized clients. and it uses JWT to do so. For those who are not familiar with what a JWT is, it stands for JSON Web Token. And it is the internal, it is the internet standard for creating data with an optional signature of the JSON payload. The payload contains information that asserts some number of claims for the client. According to the documentation, the JWT authorization should be provided in the authorization header in the HTTP request. So this is how an incoming request would look like. In step 1, the client would request to perform action X on user Y's account. It would also include the JWT authorization in the HTTP request header with claims that it is allowed to perform action X and is authorized to perform against user Y. In step 2, the sidecar, having only the knowledge of the request endpoint that was being called, check that the JWT authorization is valid and whether the client is authorized to perform that action. If so, the request is then passed on to the application. Step 3, as the validity of the JWT and the authorization of the action is performed by the sidecar, the application only needs to check if the user is authorized for that account before performing that action. During this pen test and on inspection of code, the pen tester discovered that there were 2 fields where the sidecar would extract the JWT from. There was the authorization header, as per what was mentioned in the documentation, but there was also a query parameter. And it was discovered that the request would be honored if either of the 2 fields had a valid JWT. So it allowed for the following vulnerability. The client could make a request to perform an action against an account that it was not authorized for. It would include 2 JWT tokens, one in the authorization header and one in the query parameter. It would put a valid token in the query parameter, but it would tamper with the one in the authorization header. When the sidecar receives the request and performs its check, it would determine that the token in the authorization header is invalid because it has been tampered, and the token in the query parameter is valid and it's authorized to perform that action. So as such, because of its implementation and having at least one valid token, it forwards the request to the application. And as the application is only reading the token from the authorization header, and it assumes that the token must be valid when it got to this step, it would process the tempered JWT and perform the malicious action. Now, this is technically not a bug. There is a configuration option that is available, which allows them to restrict checking of the JWT token to only the authorization header. However, that was not the default. The misconfiguration here is due to unsafe defaults. And this is just one example of how misconfiguration can occur. So here's Sam today. She creates a number of apps. The bulk of those applications code are made up of open source components which are written by someone else outside of her organization. Those applications run as containers in the cloud. So she's now wearing the operations hat, and she is responsible for managing the infrastructure for which her applications run on. As they have embedded test-driven development, she is also responsible for testing the applications to ensure that there are no bugs. And as such, she's also wearing the testing hat. And lastly, she's also wearing the security hat. As part of the you build it, you run it, and you also secure it model, she is responsible for securing her applications. Now that includes making sure that there are no vulnerabilities in the applications and the containers, making sure that the containers are security hardened. She has to do secrets management and identity and access management on there, and securing her application's parameter as part of a zero trust network. On top of that, she's now working with a shorter release cycle and needs to continuously deliver value to the customer. She's doing that not only for the system that she is working on, but also for all the previous systems and applications her team created in the past, which they are still responsible for. Now, there's a lot of responsibilities on Sam and the development team as compared to 20 years ago. So, to summarize, software development has come a long way in the last 20 years. We're now able to deliver a lot faster. Due to scaling challenges, and given that most organizations have more developers than they do for testers, operations engineers, and security engineers, we're shifting a lot more responsibilities onto the developers. We're not building our systems from the ground up anymore. Instead, we assemble them using open source components that's written by someone else. We run them on containers, which could be based off images that we don't own, and we configure our infrastructure using open source frameworks, and we run them in the cloud. As such, staying secure is hard. There's a higher likelihood of introducing vulnerabilities or misconfiguration into your system. And I believe it's not always your developer's fault. Thank you.